Hello, welcome. It's a total pleasure to be here and joining Contomac for Class 2020. What I want to try to do is cover a topic that maybe doesn't get a ton of attention in the contact lens community, and that's the idea of astigmatism for those patients that are going to be undergoing overnight orthokeratology. I really feel that this is an important topic in that clinically this can present a bit of a challenge. And what I want to try to do is demystify this as much as possible. Add some clinical tips, some pointers, some things that we can do ahead of time, even before beginning orthokeratology, to better understand what the shape of our patient's cornea is. So, the idea here in orthokeratology is to land the contact lens evenly, 360 degrees around the patient's cornea. In so doing, what we're going to be accomplishing is allowing that suction force to be equal 360 degrees around. The other thing that we're doing by landing the contact lens equally is ensuring, or hopefully ensuring, centration of the contact lens. The way in which an orthokeratology lens is constructed, if we think of it from the center out, is in the middle. That central base curve is really best thought of as the treatment curve, the mold curve. That's the curve that we're wanting the cornea to become. So we're fitting that portion of the contact lens flatter by the amount that the patient is myopic. So if we want to treat 1 diopter of myopia, we flatten the central base curve of the contact lens 1 diopter flatter than their flat K. If we're desiring to treat 2 diopters of myopia, it's 2 diopters flatter than flat K, for example. In so doing, as we make the curve, the central base curve, flatter than the curve of the cornea, what we're going to be doing is allowing that contact lens to extend out into the periphery and not land on the eye. So we need another curve in an effort to bring it back down to the surface of the cornea, namely the reverse curve. And the next curve of the contact lens is really the landing portion of the contact lens. So those really 3 main features, the central base curve, the reverse curve, and the landing area of the contact lens, comprise the modern orthokeratology contact lens. Well, if we have an eye that has a significant amount of astigmatism to it, what we're saying is that one curve, one primary meridian of that cornea has a certain shape, and then the other meridian, 90 degrees away from it, has a very different profile to it. And what we see on the slide before us here is someone who has, with the rule, astigmatism, their flat meridian being horizontal and the steep meridian running vertical. What we're looking at, though, is if we were to attempt to land the contact lens on this cornea, we have 2 very different ways of landing the contact lens on this eye. Along the horizontal, the contact lens is going to hit there first in that it's the highest, and then where the contact lens is going to lift off is the portion of the eye that's the furthest down. In this case, it's that vertical meridian, the sort of 12 and 6 o'clock position. And in a corneal contact lens that's worn for daily wear, that might be acceptable, but in the orthokeratology patient, we're wanting to land the lens equally 360 degrees around. Is a spherical contact lens going to work on an eye that's toric? So is there some clue or clues that we can pull out of either the central K values or something more broadly speaking, just the corneal topography itself? So that's the question we have here, is will a standard spherical orthokeratology design work on an eye with astigmatism? And is there something about the patient's astigmatism that gives us a clue? So what we can see here on these 2 eyes, the one on our left is an eye that has about 1.5 diopters of, with the rule, astigmatism. The eye on the right also has about a diopter and a half of with the rule astigmatism. The main difference is the area over which that astigmatism extends, in that the eye on our left really has most of their astigmatism confined to the central portion of their cornea. The one on our right is an eye that has that astigmatism running more all the way up and down, or what we would refer to as limbus-to-limbus. And if we were to attempt to land a standard spherical or rotationally symmetric orthokeratology contact lens on either of these eyes, what we could see is the one on our left, that incomplete or central, sometimes referred to as apical astigmatism, in that where the contact lens lands is out where you see this white ring, roughly that 8 millimeter chord diameter. Why 8 millimeters? Well, that's the point at which the contact lens begins to come back down to the plane of the cornea and land. That's where it's actually contacting the eye in a standard orthokeratology contact lens. So what we see here is in this incomplete or central astigmatism at that 8 millimeter chord in this patient, it's fairly symmetric. We have roughly one color running 360 degrees around this patient's eye. But what about the patient with limbus-to-limbus astigmatism? Now what we start to see here is that along the horizontal at the 12 and 6 o'clock, at the 3 and 9 o'clock positions, we have one color very different than we do at the 12 and 6 o'clock position, even though the amount of astigmatism for these two patients is roughly the same. Well, the orthokeratology fit here on the bottom really gives us some clues in that the prediction for that central astigmatism was going to be that the lens should land equally 360 degrees around, and that's exactly what happens. What about the patient on the right with that limbus-to-limbus style astigmatism? Well, unfortunately, we don't get that landing. We don't get that seal 360 degrees around. We have a bit of that fluorescein creeping in at that 6 o'clock position. So the prediction here is that the patient wouldn't get a central spherical treatment in the middle where we desire in that central base curve, that central treatment curve. Well, what if we just went ahead and had an overnight trial? What we would see with that overnight trial in the central astigmatism is things look really very good. We get that central bullseye pattern that we hope to see in overnight orthokeratology. The patient with limbus-to-limbus style astigmatism in that spherical lens construction really didn't. The lens wanted to move in that area of least resistance along the steep meridian, and in this case, in the vertical direction. The lens is pushed in the vertical direction. So the idea here in terms of the fix would be to leave the central base curve, that mold curve, spherical, in that we want the eye to become sphericalized. We want to treat their myopia as well as their astigmatism. But what we need to do is design the rest of the contact lens, the reverse curve, and the landing portion of the contact lens to be different, non-rotationally symmetric along that steep meridian. So we're just going to ask the manufacturer to make that portion, the reverse curve and the landing area of the contact lens, deeper along that steep meridian and then along the flat meridian, allowing it to land. So when do we know? When do we know that we would need a toric orthokeratology contact lens? Does topography provide us an answer? Is it purely based on K values, or is there some other piece of information, or maybe multiple pieces of information within the corneal topography that give us a clue before we even start our on-eye fitting process or even our on-eye overnight trial? Before we get too far into this, I want to give a little bit of a background on the utility of the different maps within the corneal topographer that allow us to better understand what's going to be happening in that post-orthokeratology cornea. So the first map here is really the initial kind of default display of most corneal topography systems, and that's the axial display. The axial display really has its utility in corneal topography in orthokeratology for the power. The axial display is really just that. It's a description of the corneal topography in terms of its power. It gives us the prediction of vision, how well a patient is predicted to see based off of their corneal topography. So what we have here on the screen is on the top left, we have the patient's eye before orthokeratology. On the bottom left, we have some time point after they've worn the orthokeratology contact lens overnight. That could be night number 1, could be a week later, 2 weeks later, a month later, a year later, but every single topography is going to be referenced back to that initial first baseline map. And what we see here is on the difference display, this subtractive map is the difference between those two maps. And if we click our cursor in the center of the topographical image here, what we see is this patient has 2.5 diopters of flattening. We've treated 2.5 diopters of myopia. So the axial display really is that power map. It's truly saying how much correction we got on overnight with our orthokeratology lens. The other map that has utility in orthokeratology is the tangential display. Tangential thinks about the eye a little bit differently. What it's trying to do is relate one point of curvature to another and say how does the rate of change, what's happening between those 2 points. And this is the tangential display here, giving us a better understanding of position. Where did that contact lens position in the overnight? Well, the next map here that for the purposes of our discussion in terms of astigmatism that I find the most beneficial is actually the elevation display. Now, the elevation display can be a little difficult to get our mind's eye around what's actually happening, what the corneal topographer is trying to do for us. And that is, it's treating the eye, it's making some assumptions here. How high or low do we have to go up or down in terms of physical distance? And its measurement is in terms of microns. The analogy I think of here is just like the topography map of a mountain, where if we lay that topography map out on our table and look at the map, it's giving us 2 very important pieces of information. The corneal topography map, where those lines get really close together, means the mountains change in curvature really fast, it's really steep. Where the lines on that where the lines get further apart on the mountain, the topography of the mountain means the mountain's kind of plateauing out, flattening out. But there's another piece of information on that topography map, and that is the elevation, how high or low you are. But that reference has to be taken from somewhere. And in terms of the topography map of a mountain, that reference is taken from sea level, how high or low you are in terms of sea level. What isn't initially made aware to us in terms of the corneal topography elevation display is what's sea level, what's the reference that the corneal topographer is taking it from. Now what it's doing is it's using a reference sphere, and that it's a theoretical surface that's dropped onto the eye. And what we can see here is in terms of the elevation display is that yellow arc is that theoretical reference surface. And the topographer asks a question: does it have to measure up from that reference surface sea level? If so, it's going to give us a positive value. It's saying it's above sea level by some micron amount. If though, the answer to that question, if it has to measure down from that reference surface below sea level, below the level of the ocean, it's going to give us a minus number and identify it in the blue colors. So below the level of the ocean. So in terms of our eye here on our elevation display, we have Along the horizontal, this patient has the high spot. It's measuring above along our flat meridian, and along the steep meridian in this eye with the rule astigmatism, it's measuring down.
Miru 1 month delivers one of the highest levels of oxygen transmission available in sphere, toric and multifocal Miru 1 month contact lenses from Menicon.
Let's look at another cornea here. Well, in terms of this eye with the rule astigmatism, we see on the axial display, the power display, that the flat meridian, the cool color, runs along the horizontal, and the steep meridian runs along the vertical. Well, what about in terms of the elevation display? Well, now what it's saying when it runs that reference surface through the cornea as identified by this yellow arc, it has to measure up along the horizontal by 22 microns. Or along the vertical meridian, now what it's doing is it's taking that reference surface and it has to measure down because the cornea is falling away from us. We're going below sea level in this example. By how much? 46 microns. So the difference in this particular eye is 68 microns when we compare the horizontal meridian to the vertical meridian. Well, at what point do we need a toric orthokeratology lens? Is there something that we can pull out of this height differential, or is there something even within eccentricity, or is it purely just a dioptric value amount? Well, I think for the moment, what we're going to say is that all three of those values have utility. All three of them give us clues in terms of corneal astigmatism difference, height differential, and eccentricity differential. But let's look at it more carefully. So if we think back to what we had before, that central corneal astigmatism, we're saying that most of the bend in the cornea is confined to the central portion of the eye. So we should have less height differential in the peripheral portion of the eye where the contact lens is going to land in comparison to the more Limbus-to-Limbus style astigmatism. So what do we have here? What we have up on top is an eye with central apical astigmatism of about 1.37 diopters. Well, in terms of the height differential at a chord of 8 millimeters, steep versus flat meridian, we have a difference now of 38 microns. What about an eye here on the bottom that has Limbus-to-Limbus astigmatism? This time, the patient has 1.25 diopters of astigmatism, very similar to the one that we have up on top, that apical style. But now here on the bottom, this Limbus-to-Limbus, because that astigmatism runs all the way from top to bottom through the cornea, we have a greater height differential along the steep meridian in comparison to the flat meridian. This time it's 60 microns. Even though the amount of corneal toricity as measured in the center of the cornea is roughly the same between these two eyes, we see how much height differential there really is, Limbus-to-Limbus versus central corneal astigmatism. Well, what if we looked at the eye a little bit differently? What if we looked at the eye in terms of its eccentricity? Now, it's a little difficult to get our mind's eye around what's happening in terms of corneal eccentricity. What we're saying here is the rate of change. How fast does the cornea flatten from center to periphery is really what eccentricity is telling us. So in terms of reference, a eccentricity of 0 is saying that it's a perfect sphere. There is no flattening anywhere on that eye. So the greater the number, the faster the rate of flattening. What are we looking at here? Well, in terms of the flat meridian, eccentricity is greater along the flat meridian, generally speaking. Why do we say that? Well, what we're saying is that in the middle of the eye is where the greatest steepness is in this cornea. And then along the flat meridian, the cornea flattens out, or the eccentricity goes up. What about along the steep meridian? Well, the eccentricity is less along the steep meridian. Why? Well, the eye is steep in the center, and then along that steep meridian, it remains steep. Well, let's assign some numbers to it. In terms of our apical astigmatism, we have a flat eccentricity of 0.64, and then the steep eccentricity of 0.48, or a difference between those two of 0.16. So what we're saying here is in this apical astigmatism along the flat meridian, it is steep in the center here and then flattens out more quickly along the horizontal than it does the vertical, which makes perfect sense to us because in the vertical meridian, that is our steep meridian. Now it's steep in the center and then remains steep. What about an eye with Limbus-to-Limbus astigmatism? This is someone who has their corneal astigmatism running all the way through. Well, we see a very different picture begin to emerge here. The flat eccentricity is 0.58, and then the steep eccentricity along that vertical meridian is 0.18. Very different number. What we're saying here is that it's steep and then it remains steep all the way out along that vertical meridian, limbus to limbus. So now we have a corneal eccentricity differential of 0.4, much greater than we did in the previous slide of that apical astigmatism.
Un comprobado líder en la práctica de lentes especiales y ojo seco. Cuando la precisión importa.
Hello, everybody. My name is Jason Nichols, and I'm the program chair for the Global Specialty Lens Symposium and our new meeting, the Global Myopia Symposium. We look forward to bringing you cutting-edge information each year. And again, we look forward to hosting you in 2021. Thanks, everybody.
So we have yet to answer the question, what's the threshold of requiring a toric orthokeratology lens? And studies at Pacific have taught us that sagittal differentials of greater than or equal to 30 microns is really the point at which we should probably start to think about a toric orthokeratology lens design, and that we really don't get the seal 360 degrees around like we want in a standard spherical orthokeratology contact lens. We're going to need to ask the manufacturer to differentially deepen the reverse curve and the landing zone of the contact lens in an effort to better align the cornea 360 degrees around. What about eccentricity? Well, if we're greater than or equal to 0.2 eccentricity differential in comparing those two primary meridians, that's a point at which we're probably going to want to think about a toric orthokeratology lens design. So here we see that greater than or equal to 30 micron sag differential really put to work. You start to see on that eye there with the rule astigmatism on the right in that orthokeratology lens, we really don't have that seal forming along the vertical meridian. We're going to need to differentially steepen the reverse curve and landing area of the contact lens in the vertical different than we would along the horizontal. One of the questions we have is, can astigmatism, just purely the central astigmatism, give us a clue as to when we may cross that 30 micron threshold level? And this was a study that Dr. Steve Turpin set out to answer a few years back and presented at the Vision by Design meeting. So what Dr. Turpin set out to do in these 114 eyes is measure the sagittal height differential at that 8 millimeter chord. Now again, why is 8 millimeters chosen? That's the point at which the average orthokeratology lens begins to land on the eye. And that's where we're going to want to respect that landing of the lens. Well, what you see there is on the left-hand column is a series of different corneal astigmatism values, and then the average astigmatism within those groups, and then at the 8 millimeter chord, what is the sagittal height differential? And as you start to see here, as the astigmatism value goes up, so does the sagittal height differential. But what I think is probably the most surprising to us here in this study from Dr. Turpin is, in terms of corneal astigmatism, those that had 3/4 or less, there's actually 8%, which is a surprising number of people that have 30 microns or more. But even in the 1 diopter to 1 1/4 diopters of corneal astigmatism, there's a third of those patients requiring a toric lens, and then the number really jumps up as soon as you get 1.5 diopters and above. So I think a great clinical tool here, just kind of a quick check to see, does my patient need a toric orthokeratology lens? I think it's pretty safe to say if we have a diopter and a half or more, the likelihood is almost all of those patients probably should be placed in a toric orthokeratology lens design. Well, let's look at a bit of a case example here and see the utility. We'll actually see what happens in an eye with astigmatism when we use just a spherical standard orthokeratology lens design, and then when we move over into a more toric orthokeratology lens, better aligning their cornea. So with our patient here, we have just under 3 diopters of corneal astigmatism, both right and left eye. And here we start to see, if we were to place a standard rotationally symmetric spherical orthokeratology lens on our patient, you start to see that fluorescein begin to creep in along that steep meridian at the 6 o'clock position. Well, let's just see what happens in an overnight trial. Well, unfortunately, that lens moves along the vertical meridian. We really get some decentration. Unfortunately, we don't get the astigmatism to be fully corrected. And what we would need to do is actually better align that eye with a toric orthokeratology lens, differentially treating the reverse curve and landing area of the contact lens horizontally versus vertically. So now let's give this another trial, and here you see this patient's right eye at the 2-week mark, just an awesomely well-centered contact lens and eliminating not only the patient's myopia, but also their corneal astigmatism. And then here you see side by side the standard spherical design top left and our toric design bottom right. Much better centration bottom right, much better treatment effect bottom right. And what about what happens in the patient's left eye? Well, if we go ahead and design our lens spherical top left, you really see how much lack of landing we have in that inferior portion of the lens. And then now making the lens toric bottom right, we get a much better landing. We get that kind of classic bullseye pattern, 360 degrees around, like we want in Ortho K. So now at the 2-week mark, you really start to see that patient getting full effect, and then seeing the traditional spherical orthokeratology lenses top right and the toric orthokeratology lenses on the bottom. So I think what this does for us is really start to summarize that we may get away with a standard spherical contact lens, even though the patient might have a toric cornea. I think there are some things, some clues we can get in terms of the amount of corneal astigmatism. I think there's some clues that we can get in terms of corneal eccentricity. But I think where we get the most clue is in terms of that corneal sagittal height differential taken at that 8mm chord, and then passing that value on to our orthokeratology lab partners, and then better constructing, better designing lenses to align our patient's cornea for a more successful orthokeratology outcome. With that, I'll thank you for your attention, and I hope that you all enjoy the rest of CLAS 2020. Thanks to Contomac. What a great accomplishment. Thanks so much for allowing me to be here.